We're very enthusiastic with our partnership with State University of New York to get them the best data that we can with our computational models. We have a corporate partner, Zoll Medical, that's got the transport ventilator. Most transport ventilators are very limited in their functionality and what types of ventilation modes they can deliver. So what we're trying to do is modify this ventilator. So essentially, a patient would have a real ICU ventilator available to them in a far forward location or on a military transport plane that would have all the functionality of an ICU ventilator. There's no set way to ventilate a lung. What would be good for one particular patient wouldn't be good for another patient. Despite our best intentions, when you ventilate a lung, you can cause some inflammation that may be subclinical. In other cases, it can be extremely deleterious and it can worsen existing lung injury. So we try to figure out what is the best way to push gas in and out of the lung. With our models, we can determine where those regions of overdistension and recruitment and derecruitment occur with very high fidelity that we couldn't do in an animal model. Certainly we couldn't do it in a human patient. The computational modeling that we're doing really allows us to figure out what's the best mode of ventilation we can use for a particular derangement in lung function, and how do we tailor that? So part of this, what we're doing with the computational modeling, is allowing it to run somewhat automatically. So allow the computer algorithm to determine, based on things like gas flow and pressure and oxygenation, what's the best way to adjust a ventilator for a given patient. And we can look at just a section of a subtree of the lung that will be maybe several hundred components. And just to simulate a minute or two of ventilation, even with the best computer servers that we have, takes hours to do with all the mechanical interactions and where is the gas going. So nature can do this much more efficiently than we can.